So in this first part of lectures on subsequences, we will give the basic definitions, a few examples and results, and uh, look at the proof of Bolzano-Weierstrass theorem for sequences. Okay, so first of all, let us look at what do you mean by a subsequence. In general, you will encounter this in many parts of mathematics, that whenever you define a mathematical object, you will be defining a sub of that mathematical object. One example you have already seen, that is, if you are given a set, you talk about subsets of a given set. Now the way you talk about it is that your sub object, that subset, is a set in itself, and it satisfies a property which is related to the original set. So how do you uh, uh, discuss this in case of sets is that when you are talking about subset, a set has only one basic property. If you think about it, it has a certain number of elements. So when you're talking about a subset, all you want is that every element of the subset should be an element of the original set. If that happens, then that new set is called a subset, right? So given a set, a new set is called a subset if it is at least a set, and every element of it is a element of the original one. Original set. So similarly, when you are talking about sequences and you want to talk about a sub object here, you will call it a subsequence. So first of all, it should be a sequence. Secondly, it should be related to the original sequence. So you recall that when you are talking about sequences, what is very important is that there is a certain fixed arrangement of the terms of the sequences. If you change the terms of the sequences, if you rearrange them, you get a different sequence. So when you want to talk about a subsequence, you should be able to keep that arrangement static and give a subsequence, right? Define a sequence. So how do you do this? Suppose you have this sequence x1, x2, x3, etc., where xn is the nth term of the sequence, and suppose you start looking at a subsequence of this sequence. So the first term, suppose you choose to be some n1th term of the original sequence, so it is xn1. Now the second term, when you want, you cannot go back. You cannot take terms which are less than the n1th term. So you have to choose a term of the sequence which is after the n1th term. So the second term would be some xn2, where n2 will be strictly greater than n1. This is necessary because you want to keep the arrangement of the sequence the same as the original sequence. So similarly, when you want the third term, after you have chosen xn1 somewhere and xn2 somewhere, the third term of the subsequence should be some n3th term of the original sequence, where n3 will come after the n2th term. I hope I'm making myself clear. So this is the way you will get a subsequence. And to make it more precise, what you say is that suppose you are given such a sequence, then you choose a strictly monotone increasing sequence of positive integers, n1 less than n2 less than n3 less than etc. And then corresponding to these n1, n2, n3, if you look at xn1, xn2, xn3 and so on, then that will give you a sequence first of all, and it will be called a subsequence of the original sequence, because here the arrangement of the terms is the same as the original one. You have not rearranged, you have not shuffled the terms so that here some term is coming after some other term and here it was the opposite. Nothing like that. What you are doing is that whatever was the arrangement here, from there you are choosing xn1, then xn2 is the n2th term of the original sequence where n2 is strictly greater than n1 and so on. So notice that I had talked about this notation thing that instead of writing a subscript n here after the second bracket to denote a sequence, sometimes and actually almost always for me, I am writing it as sequence xn. Okay, to make you understand that this is actually a sequence and not a singleton. Okay, so when in the case of subsequence also, I can write subsequence x and k, but now there might be slight confusion because here you notice that the indexing is now on the subscript of n. So you're choosing the n1th term, n2th term, n3th term, and so on. So what we will do is we will write it as x n k and then write this subscript k here to denote this particular thing so that there is no confusion. Okay, so this is our definition, and definitions are always made clearer when we look at examples. So let us look at our first example. This is the usual standard example which we have been seeing many times now while discussing sequences. We are just looking at the oscillatory sequence which for which all the odd terms are equal to -1 and all the even terms are equal to 1. So the sequence AN looks like -1, 1, -1, 1 and so on. Okay, so this is our given sequence, and obviously this is a bounded sequence because it takes only two values, -1 and 1. So modulus of an is actually equal to 1 for every positive integer n. So I have written less than or equal to, but actually it is equal to 1. So it is a bounded sequence also. Why am I bothering about that is because I want to somehow prepare the ground for the final result of this lecture, which is the Bolzano-Weierstrass theorem. Okay, and we have also seen that this is an oscillatory sequence. Okay, so what type of things will be subsequence of this sequence? Of any sequence actually, the easiest way is what? To look at all the odd terms. So then what you're doing, you're looking at the first term, then the third term, then the fifth term, then the seventh term, and so on. So there is no problem with this. The arrangement remains the same. So look at all the odd terms of the original sequence. That will give you a subsequence. And similarly, if you look at all the even terms of the sequence, that is, look at the second term, fourth term, sixth term, eighth term, and so on, then that will also give you a sequence, which will be a subsequence of the original sequence. So at least writing down two subsequences of this given sequence is not difficult, right? So just take the odd terms, that will give you a subsequence. Take the even terms, that will give you a subsequence. And interestingly, here, if you, in this particular example, if you look at all the odd terms, then they are actually giving you a constant sequence -1. So it is actually converging to -1. Similarly, if you look at the subsequent consisting of all even terms of the original sequence, then it is the constant sequence 1. So it is also converging to 1. So we have two questions here. The first one is that apart from these two sequences, subsequences, which we have given as an example, are there any other subsequences of the original sequence? And second question is that are there any, if there are other subsequences, are there any other convergent subsequences or not? So first of all, notice that this was just a choice that we took all the odd terms, all the even terms. This was the easiest one to choose because we could give a certain sort of formula. But there are infinitely many ways, in fact, in which you can choose a subsequence of this. For example, if you look at all terms of the form 4n plus 1, all right, so I'm again giving you a formula, say. So if you look at all 4n plus 1th terms of the original sequence, then from where will it start? If you put n equal to 1, it becomes 5, right? And then if you put n is equal to 2, you get the ninth term of the sequence. 4 into 2 plus 1. If you put n is equal to 3, then you get 4 into 3 plus 1, so the 13th term of the sequence, right? So you are getting the 5th term, the 9th term, the 13th term, and so on. So if you give this formula, that you look at all 4n plus 1th terms of the original sequence, where n is varying over the set of positive integers, you will again get a sequence. Similarly, if you look at all 4n plus 2 type of terms, then you will again get a sequence, subsequence, which is different from the even sequence. Notice, because in the even sequence you had all even sequence, meaning the subsequence consisting of all even terms of the original sequence, that had A2, A4, A6, and so on. But if you look at 4n plus 2, then what will it have? It will start with A6, right? If you put n equal to 1. Then the next term will be when you put n equal to 2. So that will be 4 into 2. So that is 8 plus 2. So 10. So after the A6th term, you get the A10th term. Then you will get 4 into 3 plus 2. So that is 14, right? So the A14th term. So you are getting a subsequence, all of whose terms are the 4n plus 2th term of the original sequence. So that is different from the subsequence which consists of all even terms, right? And similarly, you can use a random formula and you say that you get a subsequence. And you can make it more random. Don't put any formula at all. Just keep on choosing whatever way you like. Only thing you have to keep in mind, that once you have chosen a term, the next term which you choose of the subsequence has to be after that chosen term by you. So therefore you see that the number of subsequences of the original sequence is actually infinite. You can actually show that this is uncountable, but let us not bother about all those things. At least there are infinitely many ways you can get a subsequence of the original sequence. Very good. Now the next question is that can you get other subsequences which are convergent? So I hope I have convinced you that you can at least get infinitely many subsequences of this sequence. These two are just two examples. Now we are thinking of whether I can get any convergent subsequence or not. So these two we have got, right? So let us think of some other subsequence. So for example, the one which I said, look at 4n plus 2. Then 4n plus 2 gives you a formula, that is, look at all the terms of the original sequence of the type A4n plus 2, where n varies over n. So what are the values of these sequences? This particular sequence. This sequence is different from these two, right? It is, as I told you, it is very difficult to say mentally. So let us see. What was it again? It was 4 plus 2. So A6th term, then it is the A10th term, then it is the A14th term, then 4 into 4 plus 2 means A18th term, and so on. So you are getting a subset of even terms, even numbers, which is constructing the new subsequence. So there also all the values are going to be 1 itself. So that particular subsequence is also converging to 1, right? Similarly, if you look at 4n plus 1, which I had given as an example, then 4n plus 1 also is going to be consisting of all odd terms of the type 4n plus 1, right? So that is different from this one. This was all odd terms. So it started with A1, then A3 and A5 and so on. And when we are looking at A4n plus 1, where n ranges over the set of positive integers, we start with A5, let me do it correctly, then A9, then A13, then A17, and so on, right? So you can just write it down yourself. So you are again getting the terms which are all the which are odd terms of the sequence, but you're not taking all of the odd terms. So you are getting a subsequence which is different from this one, but there also the values are all equal to -1. So that particular sequence is also converging to -1. So at least I have given you examples of 2 more. You can write as many as you like. Notice, what is your example? Your example consists of a sequence which takes only 2 terms, 2 values, sorry, -1 and 1. So if it has to converge, it can converge either to, if a subsequence, sorry, has to converge, it can converge either to -1 or 1. It will not converge to any other point L, right? We had discussed this before also, and you can imagine, you want, if something converges to a number L, then you want that any epsilon neighborhood of L should contain the terms of the sequence after a certain term. So your subsequence is also at least a sequence. So if it has to converge to L, all the terms of the sequence of the subsequence after a certain term should lie in the neighborhood of any chosen neighborhood of the number L. So the number L cannot be different from 1 or -1, because if it is any other number, then there will be no, you can get a neighborhood which will not contain -1 and 1. So in that neighborhood, there will be no terms of the original sequence itself. So there is no question of any subsequence converging to it. So the only possibilities to get a limit of a subsequence is -1 and 1. So we are looking at it from the other side. Instead of trying to tell you that there are other convergent subsequences apart from the 4 I have already given as an example, 2 written in the slide and 2 I just mentioned, what I'm trying to say is I'm looking at the problem from a different angle. I'm looking at it from the angle that if I have any convergent subsequence, then where can it converge? Then it can converge to either -1 or 1. There is no other possibility that we decide. Okay. Now, if it has to converge to -1, then after a certain term, however small a neighborhood of -1 you take, all the terms of the subsequence should lie in the neighborhood of -1. So choose a neighborhood of -1 which is not containing the point 1. Take a very small neighborhood of -1, right? So whatever subsequence you take, so let us look at a concrete one. So suppose -1/2 -1 means -3/2 to half, right? So -3/2 to half is a neighborhood of -1 which will not contain 1. So in this interval, all the terms of the subsequence should land after a certain term of the subsequence. So what does that make your subsequence look like? It looks like that after a certain term, every term of the subsequence should be an odd term of the sequence. I hope I have made myself clear. If you want a convergent subsequence, then the convergent subsequence can converge only to either -1 or 1. So let us make it more specific. Suppose I try to find all subsequences which converge to -1. So if it converges to -1, then any neighborhood of -1 should contain all terms of the subsequence after a certain term of the subsequence. So if you choose a neighborhood of -1 which does not contain 1, then how can all the terms of the subsequence lie in that neighborhood of -1? The only possibility is that all the terms of the subsequence after a given finite term should be chosen from the odd terms of the original sequence, right? So in how many ways can you do? You just fix up as to how finitely many first terms, and you choose randomly there. Say for example, the first 100 terms of the subsequence, you take it to be anything from the original sequence, keeping in mind that the arrangement remains the same, right? That n1 less than n2 less than n3, etc. So the first 100 terms are chosen randomly. After that, that could be 100, that could be 50 lakhs, whatever. So first, finitely many terms, you can choose whatever you like. It can be even, it can be odd. The only thing which we keep in mind is that the arrangement of the original sequence remains the same, and after that say 100th term, you have to choose all the terms of the sequence from the uh, odd terms of the sequence. So the 100th term of the sequence, suppose, is a 500. I hope I make it clear. The 100th term of the subsequence chosen is the 100th term of the subsequence, not the 100th term of the original sequence, right? So you're choosing terms of the subsequence. So suppose you have chosen the 100th term. So that is n100 has been chosen here, right? So n100 need not be equal to 100 here. N100 could be equal to say 500. Okay, so till 100th term you have chosen whatever way you would like, keeping the original arrangement of the sequence intact. You have chosen these 100 terms of the subsequence, and that corresponds to say the 500th term of the original sequence. After that, you will have to have is that the 101th term will have to be an odd term of the original sequence. So it has to be an odd term after the 500th term of the original sequence. So it can be 503 or 505 or something. Whatever it be, it has to be an odd term. The 102nd term of the subsequence has to be an odd term. The 103rd term of the subsequence also has to be an odd term of the original sequence, and so on. So after the 100th term of the subsequence, everything, all the other terms of the subsequence have to be chosen from the odd terms of the subsequence, or odd terms of the original sequence, keeping the arrangement of the original sequence intact. So in how many ways you can do this? You can do this in infinitely many ways. The only condition you have to put is that after a finite number of terms of the subsequence, all the other terms of the subsequence will be chosen from the odd terms of the original sequence, right? So how many convergent subsequences are there of the original sequence which converge to -1? There are infinitely many. Similarly, there are infinitely many subsequences of the original sequence which converge to 1. So these are just two examples. So what are you noticing here is that there will be actually infinitely many subsequence of the original sequence. There can be infinitely many convergent subsequences of the original sequence, right? These two things are true for any sequence. In this particular example, the subsequences will converge, that is the limit of the subsequences which we will get are only two. They can be either -1 or 1. It will be nothing else. So the limit of a convergent subsequence has to be -1 or 1. But how many subsequences are there which converge to -1? There are infinitely many. How many subsequences are there which converge to 1? There are infinitely many. So I hope I have made this clear in this taking this simple example. Please keep this in mind. Okay. So next example looks a little bit more complicated, but it is not in fact. So why is it not? Let us see. Your sequence, original sequence is an, where an is equal to -1 to the power n squared divided by n squared plus 1. So as I told you in a previous lecture, whenever you have such a expression, such a fraction, then always write it in a simpler form. Just write the numerator as n squared plus 1. In this particular case, n squared plus 1 minus 1. So whatever is your denominator, you write that whenever it is possible neatly, and add or subtract a constant as the case may be. So here we get n squared plus 1 minus 1, so that this n squared divided by n squared plus 1, this becomes actually equal to 1 minus 1 by n squared plus 1. And there is a minus 1 to the power n multiplied to it. So your odd terms will look like this, because for odd terms minus 1 to the power n will become negative. So it will become minus 1 plus this, and the even terms for even n, minus 1 to the power n becomes 1. So it will look like this, 1 minus 1 by 2n squared plus 1. Okay, so how is this helpful? This is helpful in telling you many things. Notice that all the odd terms look like this. So if you focus on the odd terms of the sequence, then they are all numbers. They are taking values greater than minus 1. And if you look at the limit as n tends to infinity here, then it will be equal to minus 1. So if you look at the subsequence consisting of all odd terms of the original sequence, then it will converge to minus 1. Similarly, if you look at the even terms of the sequence, then they look like this. So if they are all numbers less than 1, and they are increasing towards 1, right? So if you take the limit as n tends to infinity, this becomes 0. So limit n tending to infinity a to n is equal to 1. So the even sequence, the subsequence of the original sequence consisting of all the even terms is also convergent, and it is converging to 1. Fine. So again, keeping Bolzano-Weierstrass theorem, which we will discuss sometime later, I want to notice that this original sequence is actually a bounded sequence. So how do you notice that? Look at any k positive integer, then 1 by k squared plus 1 is a number between 0 and 1, right? So if you add minus 1 to it, look at this expression. So if you add minus 1 to it, that number will become a number between minus 1 and 0. So in particular, all the odd terms of the sequence are going to lie in the open interval minus 1 to 0, right? Similarly, in this inequality, if you multiply it by minus 1, you get minus 1 less than minus 1 by k squared plus 1 less than 0. The inequality changes, and then you add 1. So if you add 1, what will happen? Minus 1 plus 1, so you will get a 0 here. 0 is less than 1 minus 1 by k squared plus 1 is less than 0 plus 1, so that is 1. So your terms of the numbers of the form 1 minus 1 by k squared plus 1, they will lie between 0 and 1. So in particular, all the even terms of the sequence are going to lie between 0 and 1, right? So what are you getting? First of all, you're getting that this original sequence is a bounded sequence because all its terms lie in the open interval minus 1 to 1. Not only that, it is an oscillatory, infinitely oscillatory sequence, as you can notice. Every odd term is going to lie between minus 1 and 0, and then it oscillates to the even term, next even term, which is between 0 and 1. Then it goes back to a number between minus 1 and 0, and then again back to a number between 0 and 1, and so on. And these numbers keep changing, so it is an infinitely oscillatory sequence. So what is interesting to us from a overall viewpoint is that AN is a bounded sequence, and you have at least given example of 2 subsequences of this, which will be convergent. One converges to minus 1 and the other converges to 1. Again, as I said before, that this will have infinitely many sequences, and it will have infinitely many convergent subsequences also. What you have to ensure is, if you just draw the picture here, I have not bothered to draw it, but you can see that these odd terms here, I have already depicted that it is between minus 1 and 0, and it is tending towards it. These are numbers greater than minus 1, and it's tending towards minus 1. So whenever you want a convergent subsequence, and similarly for a to n also, that a to n's are numbers between 0 and 1, and they are all increasing as n increases, and it is increasing towards 1, and the limit is actually going to be equal to 1, right? So whatever subsequence you take, this you can visualize that it will converge either to -1 or it will converge to 1. So because your sequences, there is one basic sequence which consists of subsequence which consists of all odd terms, which is converging towards -1, and there is another subsequence consisting of even terms which is converging to 1. So if you want a subsequence, another example of subsequence which converges, then that it will converge to either -1 or 1. There is no other possibility. And if it converges to -1, then what should happen is, as before, that after a certain term, all the terms of the subsequence should be chosen from the odd terms of the sequence. And similarly, if you want a subsequence which converges to 1, then that subsequence should contain consist of terms after a certain term of uh, all terms which are chosen from the even terms of the original sequence. So again, in this example, the if any subsequence converges, then it will converge to either -1 and 1, -1 or 1. So there are only two possibilities. But how many sequences can converge to -1? There are infinitely many subsequences which converge to -1. There are infinitely many subsequences which converge to 1. But the only possibility of a limit of a convergent subsequence are -1 or 1, right? As in the previous example. Okay. So let us look at a few results which will help us consider some more examples, etc. The first thing is that we have looked at two examples where the original sequence was actually not convergent. So what happens if the original sequence is convergent? Then what we want to say is that if you have a convergent sequence, then whatever subsequence of the original sequence you take, it will also be convergent, and it will converge to the same limit L. Okay, so this is almost expected if you can imagine how convergence looks like, right? Because if you have uh, limit n tending to infinity xn equal to L, it means that if you take any epsilon neighborhood of L, then after a certain term, every term of the original sequence will lie in that epsilon neighborhood. So whatever subsequence you choose, that convergent subsequence, sorry, first of all I have to show that it is convergent. So whatever subsequence you choose will have terms from after a certain term from that choice, so it will be lie automatically in the epsilon neighborhood of L. So it will be convergent and converge to L. So this was a little bit of hand waving. So instead of doing that, let us do it rigorously. So how to prove that? Consider any subsequence x and k of the sequence xn. So in the background you have this definition, right? That you have xn1, xn2, xn3 and so on, where n1 is less than n2 is less than n3, less than n4 and so on. Okay. Now you are given that limit n tending to infinity xn equal to L. So what does that mean? If you take any epsilon greater than 0, there is a positive integer n, so that for all little n greater than equal to capital N, mod of xn minus L is less than epsilon. This is from the definition, right? So this is true for this particular capital N. Now what you do is that you choose a capital K so that nk is greater than equal to capital N. What is n little k? Unfortunately, in the slide, little k and capital K look almost the same except for their size. So let us just be careful. This xnk, this nk sequence was a monotonically increasing sequence, and it was unbounded above because you were constructing a subsequence corresponding to that, right? Let us go back to the definition. See, you have this nk strictly monotone increasing sequence which is unbounded above. Otherwise, how will you construct the subsequence? So take any capital N since this little nk is an unbounded above monotonically increasing sequence, nk, you will be able to find a term of the n little k which will be greater than capital N. So that term I am denoting by n capital K. So I will be able to get a n k positive integers, so that capital K positive integers, so that n capital K is greater than equal to capital N. So once I have agreed that I will be able to get such a n capital K, then notice what happens, that if you look at little k greater than equal to capital K, then n little k will be greater than equal to n capital K, because n little k is a monotonically increasing sequence. So n little k will be greater than equal to n capital K, and n capital K is greater than equal to capital N. So n little k will be greater than equal to n capital N. So n little k is a number, positive integer, which is greater than equal to capital N. So it means that mod of x nk minus L is less than epsilon. So what have you got? That given any epsilon greater than 0, there exists a capital K positive integer, so that n little k minus L mod of that is less than epsilon whenever little k is greater than equal to capital K. So it means that limit k tending to infinity x and k is equal to L. This is what you want to show, right? Let us go back to the first slide again. Our sequence was xn1, xn2, xn3, xnk, etc. You want this sequence to converge to L in that particular theorem or result. So for that you have to choose a k, which, and so that for all little k greater than equal to capital K, mod of x and k minus L should be less than epsilon. And that is what you have been able to do here using this property, that n little k is a strictly monotone increasing unbounded above sequence, right? So we have shown this, that if your original sequence was a convergent sequence converging to L, then any subsequence of the original sequence will also be convergent, and not only that, it will converge to L. So only possibility for a limit of a subsequence will be L, and every subsequence is actually going to be convergent. So what I was trying to explain from the original, from the two examples which we saw, you can justify from this theorem also. See, there are infinitely many possibilities of getting subsequences, and in this particular case all the subsequences are convergent, so there are infinitely many convergent subsequences possible. But in this particular case, the only possible limit of a convergent subsequence is the original limit of the sequence, right? So this is finite, even though you are getting infinitely many subsequences converging to this number. So I hope I have stressed it enough. Let us look at another example from another viewpoint. So I have been saying that it is the easiest way to look at a subsequence is looking at all the even terms of the subsequence or looking at all the odd terms of the subsequence. So suppose what happens is that you are given a sequence xn which satisfies this property that limit n tending to infinity x to n is equal to limit n tending to infinity x to n plus 1 is equal to L. Okay, so I could have written x2n minus 1 here also to include x1, but it doesn't really matter. So what I'm trying to say is that suppose all the even terms of this sequence, if you look at that subsequence, that converges. Also, all the odd terms of the sequence, that also converges, and they converge to the same limit, suppose. So if they converge to the same limit, then the original sequence will actually be a convergent sequence converging to that limit L. So it is written very precisely here that if you look at these two limits and they are equal to L, then the original sequence limit n tending to infinity xn is also going to be little l. Okay, so let us prove it. Proof is again not difficult. I will advise you to think of how to prove it first and then write down the rigorous proof. It is always useful to imagine, as I said some long time back, that see what is happening is that since limit n tending to infinity x2n is equal to L and limit n tending to infinity x2n plus 1 is also equal to L, so if you take any epsilon neighborhood of L, after a certain term, all the even terms are going to lie in that epsilon neighborhood, and after another certain term, all the odd terms of the sequence are going to lie in that neighborhood, epsilon neighborhood. So if you choose a common term after which all the even terms and all the odd terms lie in the epsilon neighborhood, then that automatically implies that all the terms of the sequence will lie in that neighborhood, epsilon neighborhood, because any sequence of the origin any term of the sequence is either corresponding to an odd number or it is corresponding to an even number, right? So that is the idea of the proof. And if you write it down precisely, it will take you very little time. Suppose you take any epsilon greater than 0, then by this condition, there is a capital N such that for all little n greater than equal to capital N, mod x2n minus L is less than epsilon, right? And similarly, so I have not bothered to do that step here. So for this, you will get some n1 positive integer. For this, you will get some n2 positive integer. And you just take the maximum of that. So after a certain positive integer capital N, mod of x2n minus L will be less than epsilon, as well as mod of x2n plus 1 minus L will be less than epsilon. So if you take your little n to be greater than equal to 2n plus 1, right? So n can be even, n can be odd. So if it is after 2n plus 1, then see, this was the first one here, right? Put n equal to capital N. So x2 capital N plus 1 minus L is less than epsilon. So after that, all the odd terms, if you take, that is going to be less than epsilon. And if you take n to be some even term, say 2m or something, then 2m is greater than equal to 2n plus 1 means 2m is greater than 2n, right? So that means m is going to be greater than capital N. So x2n minus L will also be less than epsilon. I hope I have made myself clear. If you take any little n greater than equal to 2n plus 1, then what are the two possibilities for n? It can be either even or it can be odd. So if it is even, it looks like 2m, say. So 2m is greater than equal to 2n plus 1 means 2m is greater than 2 capital N. So that means m is greater than capital N. So x2m minus L will be less than epsilon, modulus of that. Similarly, if n is odd, then n will look like what? 2m plus 1. So 2m plus 1 greater than equal to 2 capital N plus 1 means that m is greater than equal to capital N. So x2m plus 1 minus L mod of that will be less than epsilon. So whether n is even or n is odd, it doesn't matter. Its modulus will be less than epsilon. So this is all you wanted, that given any epsilon greater than 0, you wanted a positive integer, which you have got now, 2n plus 1, right? Capital N came from here and then you are looking at 2 capital N plus 1. So for this positive integer, if you take any little n greater than equal to 2 capital N plus 1, then mod xn minus L is going to be less than epsilon, and hence by the definition of your limit n tending to infinity, xn is going to be equal to L. So if the even terms of the sequence converge to L, and the odd terms of the sequence converge to L, then the must converge to the same limit. Notice, this is important, and we have seen examples where the original sequence did not converge and this odd term sequence and even term sequence both converged. So there should be no confusion. If the subsequence consisting of even terms and the subsequence consisting of odd terms are both converged and converge to the same limit, then the original sequence will also be convergent and will converge to the same limit. Okay. Next result is actually an exercise, but let us do it here. It will give you some idea. So suppose xn is a bounded above sequence, okay, original sequence, and suppose little s is the supremum of the underlying set, supremum of the sequence. Then if s is not a term of the sequence, then there is a subsequence of the sequence converging to S. This is what you want to prove. Why I want to do this result is that we get used to handling subsequences. Okay, that is the only reason I am doing it. Otherwise, I could have left it as an exercise. Okay, so S is the supremum of x little n, and it does not belong to the underlying set of the uh, given sequence. So it is not a term of the sequence. Now look at open interval s minus epsilon to s. So it contains infinitely many points of the set because little s is the supremum of xn. We have seen this. So, and this is true for any epsilon greater than 0. So at least this set has to be an infinite set. That is the first observation. See, if you have a bounded above sequence, you could have just taken the constant sequence. So if you took the constant sequence, the underlying set would be a singleton, right? So it would be a finite set. So what my first observation is that if you look at the supremum of a bounded above sequence, and if the supremum is not a term of the sequence, then necessarily your sequence has to be such that its underlying set is an infinite set. It should be taking infinitely many values. So how are you going to justify that? You're saying that open interval for any epsilon greater than 0, s minus epsilon to s has to contain infinitely many points of the set uh, which is underlying to the given sequence. So just take epsilon equal to 1, half, 1/3, 1/4, and so on. So there will be a term of the sequence in the open interval s minus 1 to s. There will be a term of the sequence in s minus half to s, which may get repeated and so on. But since that is a term which is not equal to s, there will be some stage at which that particular term will be left out, right? So suppose x belongs to s open interval s minus epsilon to s, then that x may belong to s minus half to s also. It may belong to open interval s minus 1/3 to s also, and so on. But that guy x is not equal to s, so it is possible to get a positive integer 1 by n so that x becomes less than s minus 1 by n. That is what I'm stressing. So that from s minus 1 by n to s, that will also contain a point of the set, but that will be different from x. So you will be able to get some other point of the set which is not equal to the original one which you had chosen, and so on. So therefore, since this open interval s minus epsilon to s will contain infinitely many points of the set, this you know, because s does not belong to xn. So there are at least infinitely many points of the set. That's all. Okay, so this underlying set has to be an infinite set, means the original sequence has to take infinitely many values. Okay, so now let us see. First of all, what I was trying to say, that look at s minus 1 to s, this open interval. So it will contain some xn1 where n1 is a positive integer, some element of this set, so that will be a term of the sequence, so xn1. Now suppose you have chosen xn1. Look at s minus half to s. This open interval will contain infinitely many points of the set. So you, apart from xn1 also, there will be infinitely many terms. How many terms of the sequence are there before the n1th term? There are only finitely many. So since this has infinitely many terms of the sequence, there will be at least one n2 which will be greater than n1, and xn2 will lie between s minus half to s. So keep on doing this. So by induction, so keep on doing this. If you want to say it precisely, then what you say is, by induction, you choose a nk belonging to n, so that nk is greater than nk minus 1, and s minus 1 by k is less than xnk is less than s, right? And this you do for all k positive integers greater than equal to 2. Then you will get a subsequence, right? Because this is ensuring that you do get a subsequence. And the way you have constructed the subsequence, if you take the limit here as k tending to infinity, then s minus 1 by k tends to s, right? And limit k tending to infinity s is equal to s, because this is just a constant sequence. So by sandwich theorem, limit k tending to infinity, x and k will also converge, and it will converge to s, right? So you have got it by construction. So I hope I have made myself clear. So whatever you have proved for a bounded above sequence is this same result is true for bounded below sequence also. Let us do it quickly. That suppose you have a bounded below sequence, and suppose little s is the infimum of xn. So if little s is not a term of the sequence, then you will be able to get a subsequence of xn which converges to s. So let me just first prove this, and then explain why this not being a term of the sequence becomes important. Okay, so suppose I'm looking at this bounded below a sequence, and its infimum is not a term of the sequence. So again, as before, what can you say? That since s is a infimum, actually I need not have spent so much time on this. We have discussed this when we talked about infimum and supremum, that if little s is not an element of the set, where little s is the infimum of the set, then for any epsilon greater than 0, open interval s to s plus epsilon contains infinitely many points of the set. So at least the set is infinite, otherwise how will it contain infinitely many points of the set? So the original sequence has infinitely many values, right? That is at least true. Okay, why did I have to do this? I am not very sure. Okay, it's okay. So let us see. So then what you will do is you start constructing as you did in the previous result, that you first take epsilon equal to 1, then look at the open interval s to s plus 1, that will contain a term of the sequence called, let it be the n1th term. Choose one, there will be infinitely many. So choose one and call it, let it be the n1th term. So you have done this, and once you have done this, then by induction you keep on choosing the next terms of the sequence. So after you have chosen this n1th term of the sequence as the first term of the subsequence, then you look at the open interval s to s plus half. Then this open interval s to s plus half will contain infinitely many points of the set. So and there are only finitely many terms of the sequence before the n1th term. So you can always get n2 which is greater than n1, so that xn2 also belongs to the open interval s to s plus half. So choose that and look at xn2. So you have constructed the second term of the you have chosen the second term of the subsequence. Similarly, you keep on doing it for every k positive integer greater than equal to 2. Then you will get a subsequence, and it is sandwiched between two sequences. One is the constant sequence s, the other is the sequence s plus 1 by k, which converges to s as k tends to infinity. So limit k tending to infinity, x and k will also be equal to s. So this is by construction. Now why is this important, that s should not be a term of the sequence? For example, you look at the sequence 1, 2, 3, 4, etc. Then this sequence is monotonically increasing, diverging to infinity. So your xn is 1, 2, 3, 4, etc. So it is bounded below. It is bounded below by 1. But can you get a subsequence which converges to 1? No. Your sequence is 1, 2, 3, 4, and so on. So any subsequence of that will also be a strictly monotonically increasing unbounded above sequence, right? So you can never hope that a subsequence of the sequence 1 2 3 4 etc. will converge to 1. No possibility. So this is a very, very important condition which you put here. Similarly for the previous one, if you take a bounded above sequence and you suppose that S is the supremum of that, then if S belongs to the is a term of the sequence, then it may not be possible to get a subsequence which converges to it. For example, take the easiest one, look at 1 by n, right? So 1 by n, the original sequence is actually converging to 0, right? And it is also bounded above. It is bounded above by 1 because your sequence is 1 half, 1/3, 1/4 and so on. So it is bounded above by 1, but obviously since this sequence is converging to 0, every subsequence of this is converging to 0. There is no possibility of any subsequence of this converging to 1. So this condition that the supremum should not be a term of the sequence is essential to do this result. Okay. So finally, our coup de grace, as we say, is the Bolzano-Weierstrass theorem, which says that every bounded sequence in R has a convergent subsequence. So this is where I was trying to reach. So how will we prove this? We will use nested interval theorem very crucially here. Okay, so let us see. So I want a bounded sequence. Let us choose a bounded sequence xn. Since it is bounded, there is a positive integer, not integer necessarily, there is a real number capital M, so that mod xn is less than M for all little n greater than, for all positive integers little n, right? So that means what? The way I have chosen M is that mod xn is less than M for all little n positive integer. So that means that xn lies in this open interval minus m to m. This was not necessary. I could have taken less than or equal to also, but it is okay. So now you have that all the terms of the sequence lie in this open interval minus m to m. You consider the closed interval minus m to m. Okay. And you take a subdivision of it. Subdivision of it means just consider it as a union of two subintervals of equal length whose union is the original one. And since you want two subintervals of equal length whose union is the original closed interval, it has to be like this, right? You have to take the midpoint of minus m to m, which is 0, and then look at the closed interval minus m to 0 or closed interval 0 to m. Now, since you have a sequence, obviously this is an infinite sequence. We have not talked about finite sequences at all. So infinitely many terms of the sequence will belong to either close interval minus m to 0 or close interval 0 to m, or to both, right? But it has to happen that at least one of them will have infinitely many terms of the sequence. Because if both of them had only finitely many terms of the sequence, then the union would also have only finitely many terms of the sequence, which is not possible, right? So both of the subintervals will have, either of the two subintervals will have infinitely many terms of the sequence. At least one of them will have. So choose one of them which has infinitely many terms of the sequence. Call it I0. All right. So what is going to be the length of I0? I have used the same notation as before. I have used mod I0 to denote the length. Length is going to be m, whether it is this one or this one, right? 0 minus minus m is also m. M minus 0 is also m. Okay. And equal parts we have divided. So it's obvious the original sequence had length, original interval had length 2m. Now the interval has length m. Now this is a subinterval which has infinitely many terms of the sequence. So choose one term from that, call it xn0. right? So choose one of the terms of the sequence, choose the n0th term of the sequence. That is what I'm trying to say. Okay, you have done this. Now again, what you do is you have this I0, right? So you again subdivide it into two equal parts, two equal subintervals. Then since I0 has infinitely many terms of the sequence, these subintervals will also have will have the property that either of these will have infinitely many terms of the sequence for the same reason, because if both of the subintervals have only finitely many terms of the sequence, then I0 will also have only finitely many terms of the sequence. But I0 has infinitely many terms of the sequence. We have chosen I0 such. So therefore, when I'm subdividing I0 into two subintervals, then at least one subinterval will have infinitely many terms of the sequence. So you choose one of these subintervals and call it I1. So I1 has infinitely many terms of the sequence. And how many terms of the sequence are less than the n0th term? There are only finitely many. So you can always get a term of the sequence indexed by n1, say, where n1 is greater than n0, right? n0. So you choose such a term, call that xn1. So choose a xn1 so that n1 is greater than n0, right? So you have got this, and what, let us just keep track of the length of the intervals, because I told you that we will be using nested interval theorem. So what is the length of I1 now? It is half of the length of I0. What was the length of I0? The length of I0 was m. So what is going to be the length of I1? It is going to be m divided by 2. And not only that, I1 is a subinterval, so I1 is a subset of I0. So you see where we are going. We are constructing a nested sequence of intervals, closed intervals, whose lengths are decreasing, and we are also choosing these points, right? So let us see how where can we go with this. So suppose we have chosen I0, I1, etc. till IR. Okay, so that what happens, the length of IK is equal to capital M divided by 2 to the power k, right? At each stage it will become half of the length of the previous one. So therefore originally I0 had length M, so therefore I1, when we chose, it had length m by 2. What will be the length of I2? It will be half of m by 2. So it will be m by 2 squared. And again, what will be length of I3? It will be half of m by 2 squared. So it will be m by 2 cube, and so on. And not only that, the way we are choosing it is that IK has infinitely many terms of the sequence, right? So that is the way we keep on doing it. First I0 had infinitely many terms at the first stage, then you subdivided I0 into two subintervals, chose one subinterval which had infinitely many terms, called it I1. Do the same thing again, subdivide I1 into two, choose one which has infinitely many terms of the sequences and call it I2, and so on. So each IK has infinitely many terms of the sequence, and IK is a subset of IK minus 1. This we are doing, and not only that, we are also continuously choosing terms of the sequence x and k in IK so that nk is greater than nk minus 1. This we are doing by the reason, this we are able to do because each ik has infinitely many terms of the sequence, and before any nk minus 1th term there are only finitely many terms of the sequence. So it is always possible to choose a nk which is greater than nk minus 1 so that xnk also belongs to ik, right? So what we did in the first two steps, in the induction step, we assume that this is true and prove that for the next one also we will be able to get the same thing. So I'm not repeating this line by line. You have understood, I think. You have done till IR, then you subdivide IR into two subintervals of equal length, then at least one of the subintervals must contain infinitely many terms of the sequence. Otherwise IR would not contain infinitely many terms, right? So At least one of the subintervals will contain infinitely many terms. Choose one of them and call it IR plus 1. Then you already have xn1, xn2, etc. till xnr. So till the nrth term, there are only finitely many terms of the sequence. So it is possible to get a nr plus 1th term of the sequence also, which will be contained in IR plus 1, because IR plus 1 has infinitely many terms of the sequence. So take that nr plus 1th term, fix up, and notice that what has happened is that IR plus 1 is a subset of IR, first of all, by your choice. And not only that, its length has become half of the length of IR. So the length of IR was m divided by 2 to the power r, and now you're looking half of that. So it has become m divided by 2r plus 1. Very good. So at least you have constructed a sequence of closed and bounded uh, intervals whose lengths form a null sequence, right? If you look at limit k tending to infinity, m divided by 2 to the power k, that will be 0, right? So you do have such a thing. Not only that, you have also constructed a subsequence xnk of the original sequence xn, so that xnk belongs to ik for every uh, non-negative integer, right? For k 0, 1, 2, 3, etc. Now, nested interval theorem tells you what? Nested interval theorem tells you that if you look at the intersection of uh, all these intervals, closed and bounded intervals, then it will be equal to a singleton. So there is a unique number x which belongs to intersection n equal to 0 to infinity in. This is your nested interval theorem telling you. And how does this help me? This helps me because if I look at xnk minus x, then xnk belongs to ik, and x also belongs to ik because x belongs to the intersection. So if you look at the length of uh, the distance between x and k and x, that is mod of x and k minus x, then that will be less than the length of the ikth interval. So that is that it is going to be less than m divided by 2k. So what is happening is you are getting 0 less than or equal to mod x and k minus x less than m divided by 2 to the power k. M by 2 to the power k is a sequence which is converging to 0. 0 is obviously the constant sequence converging to 0. Therefore, limit k tending to infinity mod x and k minus x is equal to 0 by sandwich theorem. So that means what? That limit k tending to infinity x and k minus x is equal to 0. We saw this, that if the absolute value of a sequence if the sequence consisting of absolute values of a sequence is a null sequence, then the original sequence is also a null sequence. So you get limit k tending to infinity x and k minus x equal to 0. But x is a constant, right? So what does this mean? That limit k tending to infinity x and k is equal to x. So after some deliberations, what have you proved? You have proved that if you had a bounded sequence in R, then it will always have a convergent subsequence. This is what you have proved, and it is called the Bolzano-Weierstrass theorem. And if you remember, there is a Bolzano-Weierstrass theorem for sets also. We had proved it some time back. So what did that statement say? That if you look at an infinite bounded subset of R, of the set of real numbers, then that infinite bounded set has to have a limit point, right? So this theorem can also be proved using nested interval theorem. We did not do it then because we did not know how to prove nested interval theorem at that particular stage of time. But now that you have learned what is how to use not only what is nested interval theorem, how to use nested interval theorem to prove Bolzano-Weierstrass theorem for sequences, you can follow the similar type of argument to prove it for sets also. And that is going to be your assignment. that you have to use nested interval theorem and prove Bolzano-Weierstrass theorem for sets. That is, use nested interval theorem to show that every infinite bounded subset of real numbers has a limit point. So this is your assignment. Okay. So let us look at one example now again. So my sequence an is equal to 1 minus 1 by n sine n pi by 2. So I am going to use some properties of the sine function here. So what is this sequence going to look like? If your n is 1, then 1 minus 1 is 0, right? So it becomes 0. Okay. Even though sine pi by 2 is 1. If your n is an even integer, then it will look like what? Some 2k. So 1 minus 1 by 2k is fine. It is going to be a number less than 1. What happens to this? This becomes sine 2k pi by 2. 2 and 2 cancels out. So it becomes sine k pi. Sine k pi is 0. Right? For whatever k you take, value of k. Here it is only positive integers, but k, any integer, sine k pi is going to be 0. So you get a 0 here. If you are confused with this, just bear with me for some time and then I will tell you why do you get this. What happens when you take n to be an odd integer? Then you can show that sine 2k plus 1 pi by 2 is equal to minus 1 to the power k. Again, for the time being, you just bear with me. I will explain why this is equal to minus 1 to the power k. So the value will be equal to minus 1 to the power k, that comes from the sine function, times 1 minus 1 by 2k plus 1, right? So this is your sequence. So obviously this sequence does not converge. Why? Why is it so obvious? It is because every even term goes to 0 and every odd term is hovering around either 1 or minus 1. Right, depending on the k. Now if k is even, then it will be this thing will become positive, so it becomes 1 minus 1 by 2k plus 1, and if k is odd, then it becomes minus 1 plus 1 by 2k plus 1, right? So depending on k, these terms are either near 1 or near minus 1, and every even term and the first term of the sequence is equal to 0. So there is obviously no chance of this sequence to converge, but at least it is bounded. Because if you take the mod of this, 1 minus 1 by n is a number which is less than 1, and modulus of sine x is less than or equal to 1. Right? So sine takes values only from minus 1 to 1. So therefore, your terms of the sequence lie in the closed interval, or rather, lie in the closed interval, open interval minus 1 to 1 actually, because if you take the modulus of this, that will become less than or equal to 1 minus 1 by n, because this is less than or equal to 1, but 1 minus 1 by n is always less than 1, right? Except for the first one. Okay, so maybe I should have written less than equal to, or I should have written for all n positive integer greater than equal to 2. So the sequence is bounded. So what does your Bolzano-Weierstrass theorem tell you? It tells you that an should have a convergent subsequence. So let us verify that for this particular example. So it is clear, first of all, this one is the easiest one, that if you look at the subsequence consisting of all the even terms of the sequence, that is going to be 0, constant sequence 0. Excuse me. So its limit is also going to be 0. So at least you have got 1. And actually, let us look at all possibilities. So as I said, for the odd terms, except for the first one, all the odd terms are either near 1 or near minus 1. And the way we are getting the expression, we can see that if we take our k to be odd, right? So what will it look like? It is going to be 2 times some 2m plus 1. So it will be 2 into 2m, so 4m plus 3 type of thing. So if I take k to be odd, means if I look at 4n plus 3 type of terms, then I will get a minus here, and so that subsequence is going to converge to minus 1. And if I look at k to be even, so it is some 4m, so then it will look like what? 2 into 4m plus 1, so it looks like 4n plus 1, right? I have written that down carefully here. So if I take k to be even, then the final terms are 4n plus 1 type of indexed by 4n plus 1, where n is a positive integer, and they will converge to 1, because this becomes 1, and 1 minus 1 by 2k plus 1, as you take k tending to infinity, it goes to 1. So this will go to 1, this subsequence will go to minus 1, and this subsequence will converge to 0. Okay, so as I had mentioned in the beginning of this lecture, these are the only 3 possibilities actually. So use a little bit of mathematical intuition here, because if you try to write down everything carefully, then it is going to become a huge thesis type of thing. So let us not do that. You can just understand now that this particular sequence is converging towards 1, this particular sequence is converging to minus 1, and this sequence is converging to 0. And if you look at the terms of the sequence, they're either going to be odd terms, even terms which look like this, or they are going to be odd terms, and odd terms will have either this expression a4n plus 1, or it will have the expression a4n plus 3. So your original sequence is partitioned in 3 subsequence, so to say. One subsequence consists of all even terms, which is converging to 0. One subsequence which consists of all terms of the form a4n plus 1, which converges to 1. And one subsequence which converges to minus 1, whose terms are of the form a4n plus 3. So, and any term of the sequence is going to look like this or this or this. So therefore, I'm saying that we have partitioned it, right? And these are the only 3 possibilities you get by partitioning the original sequence. Therefore, the only possible limits of a convergent subsequence are going to be 0, 1, and minus 1. Even though there are going to be infinitely many subsequences which will converge to 0 or 1 or minus 1. So the limits which you will get will be only these 3. This I'm doing it in anticipation of the next lecture, but for the time being, if you needed only to verify your Bolzano-Weierstrass theorem, this was sufficient. But we observe more than that in this particular example. Okay, so as I said, let me just quickly go through what are trigonometric functions. Obviously, I'm not going to give you a definition of that here, because we still need to do lots of work before precisely defining what sine x is or what cos x is, first of all, and then later on the rest of the trigonometric functions. So why do we need some work? There are two ways of describing them. One is using power series, which we have not yet learned, and the other is using integration, the theory of which we have not yet learned, right? Even though you know how to integrate. So, and actually you have been using sine x and cos x since your high school at least. So you know these properties. I'm not going to go into the details. This I have written down just to emphasize that all these 5 properties actually categorize sine x and cos x. That is, if you have 2 functions which satisfy these properties, that sine 0 is 0, cos 0 is 1, sine pi is 0, cos pi is minus 1. So some special points will have these values. Sine pi by 2 is 1, cos pi by 2 is 0. This is one set of conditions which you want to put on the functions. The other one is that it is 2 pi periodic. The third one is that if you take the square and sum, that is sine square x plus cos square x, it is going to be equal to 1 for all x. Also, you want that there is this addition formula or subtraction formula you like for cos. cos of y minus x is equal to cos y cos x plus sin y sin x, and an inequality. All these are just straightforward for you, I think. And this one also is true. If you put this categorize restriction, then the only functions which you will get is the familiar sin x and cos x, which you have in, which you know about. At least you can apply them in various situations. At least you know that. So what is this inequality? It is telling you that 0 is less than cos x is less than sin x by x is less than 1 by cos x when x lies between 0 and pi by 2. Right? So this inequality we will need after some time. So all these properties, if any two functions satisfy all these 5 properties, then they have to be the sine function and the cos function. Okay, so in the next slide, I have just tried to draw the graph of sine and cos. You can see the blue line is the blue graph is the sine function, and the red graph is the cos function. And you can see that at various values, what is it taking? At various points, what are the values taken by the graph? Okay, so once you have sin x and cos x in hand, you can define other trigonometric functions also. But before that, let us just go quickly through these properties. These are not difficult at all. You have cos y formula for cos y minus x, right? So put y is equal to 0 there. Then what do you get? You get cos of minus x is equal to cos x, because cos 0 is 1 and sin 0 is 0. So cos of minus x is equal to cos x. This is what you get. Similarly, if you put put y is equal to pi by 2, then cos pi by 2 minus x is going to be sin x. Again, sine of minus x is going to be equal to minus of sin x. I'm not going into the detail of this. Okay, cos pi by 2 cos x, that will become 0 because cos pi by 2 is 0, plus sin pi by 2 sin x. Sin pi by 2 is 1, so this is sin x. Similarly, for this one, you write down sine of minus x equal to cos pi by 2 plus x. No problems with that. And then you just write it as cos pi minus pi by 2 minus x and expand and so on. So you will get minus sin x. So sine of minus x is minus sin x and cos of minus x is cos x, right? And you will also get this formula. Just write y minus minus x, so you'll get the addition formula for cos. Similarly, you will get the addition formula for sine by using the relation between sine and cos. This relation, that sin x is equal to cos pi by 2 minus x, and similarly you will get the subtraction formula for sine using this one, right? Using this one and cos phi minus x's formula, you will get all these results are just straightforward. Okay, now what where I wanted to stress was this particular thing, which you might not know, or you may know also. It let me just give the proof. So cos k pi is minus 1 to the power k. This is actually true for every integer, if you like, but that is ridiculous. So let us just talk for positive integers, because it will automatically happen there. It just becomes 1 by something. So let us just talk about positive integers. Then cos k pi is minus 1 to the power k. So how will you prove this? First of all, you know that cos pi is equal to minus 1. Oh, there is a typo here. This is minus 1, right? And suppose that cos m pi is equal to minus 1 to the power m. Then what is cos m plus 1 pi? We know by the addition formula, it becomes cos m pi minus sin m pi sin pi. Cos pi is minus 1. Cos m pi is minus 1 to the power m. So it becomes minus 1 to the power m into minus 1 minus, and sin pi is 0. So this part is just 0. So you just are left with minus 1 to the power m into minus 1. So you get minus 1 to the power m plus 1. So cos k pi is equal to minus 1 to the power k for every positive integer k. You have to remember this. Okay. And what is sine 2k plus 1 pi by 2? That is also equal to minus 1 to the power k for every positive integer k. right? So that I needed here, remember? So I'm going to just prove that. So let us see. How are you going to do it? Look at sine 2k plus 1 pi by 2. What does this mean? This 2 cancels out, right? So it becomes sine k pi plus pi by 2. Use the addition formula for sine. So you get sine k pi cos pi by 2 plus cos k pi sine pi by 2. So what is cos pi by 2? That is 0. So this first term is actually 0. And what is sine pi by 2? That is 1. So this second term is just cos k pi, and which you have already proved to be equal to minus 1 to the power k. So this is true, that cos k pi is minus 1 to the power k, and sine 2k plus 1 pi by 2 is minus 1 to the power k for every positive integer k. And this final one is actually a theorem which says that mod sine x is less than or equal to mod x for all x in R. So remember your categorization. Here you had some such thing, right? So sine x by x. So using this and some other properties, we can prove this theorem. But unfortunately, I'm going to need some basic results. So right now I'm not proving in this particular statement, but we will believe it, take it on faith. And when we do power series, or when we talk about integration, then I can justify that this is actually true, that mod sine x is less than or equal to mod x for all x in R, for all real number x. Okay, so as I said, that once you have this sin x and cos x, then you can define several other trigonometric functions by taking suitable rational functions constructed out of that. I don't want to call them rational function. Okay, so just look at sin x by cos x, for example. So then we call this tan x. So this function will be defined where cos x is not 0. So whenever cos x is 0, this will be undefined, and in fact, it has a uh, limit tending to infinity from the right. Just look at pi by 2, for example. So it goes to infinity from the right, from the left hand side of pi by 2, and from the right hand side of pi by 2 it tends to minus infinity. So there is a unboundedness here. We will discuss this when we talk about sequences. So tan x's graph looks like this. Similarly, you can talk about cosec x, which is just 1 by sin x. It is defined whenever sin x is not 0. So that means if x is equal to k pi, you cannot define this function. So cosec x is defined only for 1 by sin x. Uh, Cosec x is equal to 1 by sin x for all x not equal to k pi. So here also the graph breaks down at several points, as in the case of tan x. Similarly for sec x, which is 1 by cos x, it will be not defined when cos x is equal to 0. So that is when x is equal to 2k plus 1 pi by 2, then it will not be defined. So it is a breakage like this, I'm sorry. So this is the graph of sec x. And similarly, you can talk about cot x, which is 1 by tan x, that is cos x by sin x. So this will be defined only when sin x is not 0, that is only when x is not equal to k pi. Okay, and then there are several formulas of trigonometric functions which you have been using since your high school. So we will be also using them whenever we do a certain number of problems. And in the next lecture, we will go on to talk about subsequential limits and their importance. We must stop now.